a strong interaction among the bodies involving exchange of momenta during collision in a short interval of a time. If an alpha particle is moving in the direction, in this path a stationary nuclei is present. Among these particles, Coulombic forces presents. Because of this reason, the alpha particle cannot directly in contact with the nucleus. But in the presence of the nucleus, the path of the alpha particle is deviated. So we can conclude that the exchanges of momenta, that is a transfer of momenta, is possible. That is also called as a collision. Depending upon the direction of motion of colliding bodies, collisions are divided into two groups. Number one is one-dimensional collision or head-on collision or direct collision. Number two is oblique collision. Depending upon the total kinetic energy of the conservative system, collision of the bodies is divided into two groups. Number one is elastic collision. Number two is inelastic collision. For the clarification of one-dimensional collision, you can find out the first. If a body of mass m is considered, its center of mass is at the center. If the body moves in direction, the line of motion of a body is taken in a direction with a speed u. Another body of mass m2 the center of mass is there. The line of motion of a body is there. If they are moves in a direction as represented in figure, if velocity of the first body is greater than the velocity of the second body, the line of motion of the body is represented in the diagram. After some time, the bodies are impact. Due to the impact, the direction of the velocity vectors does not change. Even though collision is possible, then the type of collision is called as one-dimensional collision. That means after collision, both the bodies A and B are moves in the same direction, cannot change its direction, but its velocity changes. Mass of the body remains constant. The force due to collision for both the bodies acts before and after collision are in the same direction. Such type of collisions is called as one-dimensional collision or head-on collision or direct collision. That means before and after collision, the velocity vector directions does not change. they are along in the same straight line. That is called as one-dimensional collision. Number 2, oblique collision. The body A is center of mass is there. The line of motion of body is directed in this figure. Line of motion. If a body A is there, the line of motion of a body is represented in dotted lines. Another body B. The direction of motion of a body is in the direction of during collision, a line passing through common, normal to the colliding bodies during impact. That line is called as line of impact. Line of impact. The line of motion of body A is this direction. Line of motion of first body. Line of motion of second body is there in direction. Due to the impact, due to the collision, a common line is drawn. A line is passes to the common. For both the common passes through center of masses. Normal to the surfaces are in contact during collision. That line is called as line of impact. Or you can write this direction also. If a body is here, moves in direction, body is moving this direction, the line of impact is through this direction. So, depending on the line of impact, representation of line of impact. For example, another example is there for an inclined body. It is on one surface. In this, a body is rolls. This is the center of mass of the body. This is the line of rotation or line of motion of a body. Two surfaces are in contact. A line of impact, normal to the surface, will pass in the center of mass. So this is the line of impact. For both the bodies, motional bodies, the forces are acts along the line of impact. So, in this direction, in oblique collision, body moves in a plane. Either it may be two-dimensional or three-dimensional. So, in an oblique collision, bodies moves in two-dimensional or three-dimensional motion. Next, it is the conservation of total kinetic energy. The collision is divided into two groups. Number one is elastic collision. Another one is inelastic collision. Elastic collision means the collision in which only momentum and kinetic energy, both are conserved. But in elastic collision, only momentum is conserved, but not of K. Kinetic energy is not conserved. So we want to discuss elastic collision and inelastic collision. Here both momentum and kinetic energy is conserved. Examples are collision among the atomic molecules, atoms, between the two atoms, or collision between two billiard balls, smooth collision between the two billiard balls, in which both momentum and kinetic energy is conserved. Other forces may be present, it's not an influence, but in a system two or more particles, both of them are conserved. In inelastic collision, only momentum is conserved in each and every stage, but kinetic energy is lost. So we want to discuss, in this class, I want to discuss one-dimensional elastic collision. In this elastic collision, we can classify it into two groups. Number one is semi-elastic collision. Number two is perfectly inelastic collision. So today I want to explain perfectly elastic collision in a one-dimensional. Let's consider two bodies having masses m1 and m2 are moving in the same direction with an velocities u1 and u2 before collision. If we can consider u1 is greater than u2, after some time, first body is impact with the second body. So the two bodies are moves different velocities in the same direction. The line of motion is in the right direction. So line of impact is also lies in the same direction. Line of impact is in the dark line. Line of motion is written dotted lines. Before and after collisions, the bodies, two bodies moves with different velocities but in the same direction. We can consider as an one-dimensional head-on or elastic collision. So, in elastic collision, two quantities must be conserved. Number one is momentum. According to law of conservation of linear momentum, you can conclude that the momentum of a system before collision is always equal to the total momentum of the system after collision. So the momentum of the first body is m1 u1 They are in the same direction. So second body is m2 u2. Momentum is mass into velocity. They are in the same direction. So we cannot represent it by an arrow marks. Is equal to sum of the momentum of the bodies after collision. So simply we can write as in a vector notation. If the direction is clearly mentioned, if direction is not cleared, then simply you can write as a vector notation. M1 of U1 minus V1 is equal to M2 of V2 minus U2. We taken as equation 1 according to law of conservation of linear momentum. Number 2, according to conservation of kinetic energy, law of conservation of kinetic energy, simply we can write as kinetic energy means half mu square, m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. So simply we can write as m1 of u1 square minus v1 square is equal to m2 of v2 square minus u2 square. Equation 2. One dimensional non-elastic collision. Non-collision. So equation 2 by equation 1 simply we can get as u1 square minus v1 square divided by u1 minus v1 is equal to, if direction is not given, then we can simply write as vector notation. If already the direction is taken as, so we can write it as a scalar notation, is equal to v2 square minus u2 square divided by v2 minus u2. A square minus b square. So a plus b into a minus b. So simply we can write as u1 plus v1 is equal to v2 plus u2. v2 plus u2. So from this one, we can simply write as u1 minus u2 is equal to v2 minus v1. If direction takes place. If direction is not given, it declares a vector notation. That means, if a body 1 is approaches to the second body, the relative velocity of approach before collision, u1 minus u2 means the relative velocity of approach before collision is equal to the relative velocity of separation after collision. After collision, the bodies are separate to each other. Their masses are conserved, but velocities are changed. So finally we can conclude that in case of one-dimensional head-on elastic collision, finally we can conclude that the relative velocity of approach before collision is equal to the relative velocity of separation after collision. From this expression, simply we can find out the velocity of the first body and second body after collision. So I want to find out first the velocity of the first body after collision. So from this equation, simply we can write as v2 is equal to u1 plus v1 minus u2. By substituting this value in equation 1, 3 in 1, simply we can write as m1 of u1 minus v1 is equal to m2 of v2 minus u2. v2 means u1 plus v1 minus u2 minus of u2. So from this expression, simply we can write as m1 u1 minus m1 v1 is equal to m2 u1 plus m2 v1 minus m2u2 and also minus m2u2. So from this one we can write as m1u1. Here also m2u2, we can write this side minus m2u1 is equal to m1v1 plus m2v1 minus m2u2 minus m2u2 minus 2m2u2. So simply we can bring this action m1 minus of m2 into u1 plus 2m2u2 is equal to m1 plus m2 into v1. And finally, the velocity of the first body after collision v1 is equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 divided by m1 plus m2 into u. So in case of one-dimensional elastic collision, the velocity of the first body after collision is expressed in the form of this one. In a similar pattern, if from this equation we can write as v1 is equal to v2 plus u2 minus u1. So equation 4 is substituted in equation 1. Then from equation 1 simply we can write as m1 of u1 minus v1 means v2 plus u2 minus u1 is equal to m2 into v2 minus u. So m1 u1 minus m1 v2 minus of plus minus m1 u2 minus of minus plus m1 u1 is equal to m2 v2 minus m2 u. Similar terms are taken as the same side, then simply we can get as here m1 u1, here also m1 u1. So 2m1 u1 here minus m1 u2, here is minus m2 u2, we can take on this side, then plus m2 u2 minus m1 u2 is equal to, this moves in direction, we can take as a positive m1 v2 plus already have there m2 u2. So if we take as a common u2, then m1 2m1 u1 plus m2 minus m1 of u2 is equal to m1 plus m2 of v2. So the velocity of the second body after collision is represented by an expression v2 is equal to 2m1 by m1 plus m2 into u1 plus m2 minus m1 by m1 plus m2 into u2. This equation 5 and 6 expressions both are gives the velocity of the first and second bodies after collision in a one dimension. So I want to explain the special cases depending upon mass of the bodies and velocity of the bodies. These are special cases. So Finally, in case of one-dimensional elastic motion, elastic collision, the final expressions, that is the velocity of the first body after collision, is given by equation v1 is equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 divided by m1 plus m2 into u2. And velocity of the second body after collision is given by 2m1 by m1 plus m2 into u1 plus m2 minus m1 by m1 plus m2 into u2. From these two expressions, I want to discuss special cases. So there is no requirement of this expression. Finally, I can give the applications from this formula. First one, application. If both the bodies having same masses, that is m1 is equal to m2, just taken as a m, then the velocity of the first body after collision, that is for equal mass of the two bodies, collision between the equal mass of the two bodies, then velocity of the first body is given by, here both bodies, by substituting these expression, these values in this expression, then m1 and m2 both are same, so v1 is equal to 2m divided by m plus m, 2m into u2. So simply we can get as u2. And v2 is equal to 2m divided by m plus m, 2m into u1. Here m2 and m1 is same, so you can take it as 0, so you can take it as u1. Simply we can conclude that the velocity of the first body before collision is equal to the velocity of the second body before collision, and the velocity of the second body after collision is equal to the velocity of the first body before collision. That means exchange of momenta takes place among the two equal massive bodies u1 and u2 in the same direction. After impact, exchange of their momenta takes place. That is, first body moves with an velocity of the second body before collision, and the second body moves with an velocity equal to velocity of the first body before collision. That is, the exchange of momenta takes place. For example, four bodies on a horizontal surface. Body 1 is there, 2, 3, 4. Both of them are same massive bodies. These three are at rest. First body moves in this direction with a velocity u1 in a one-dimensional elastic collision. If it is collided with the second body, automatically exchange of the momenta is possible. So first body comes to rest and second body moves with a velocity u1. The second body is collided with the third body, automatically exchange of momenta takes place. So second body comes to rest and third body moves with a velocity u1. Finally, third body is collided with the fourth body, automatically exchange of momenta takes place. So third body comes to rest and fourth body moves with a velocity u1. And finally, we can conclude that first body, second body, third body comes to rest after collision. Fourth body moves with a velocity u1. This is the exchange of momenta, exchange of their velocities, and also exchange of momenta takes place between the two same massive bodies in case of one-dimensional elastic collision. If the second body is at rest, bodies must have same, both the bodies having same mass, but second body is at rest, then automatically velocity of the first body, I want to find out the velocity of the first body. So by substituting the values, both are the same masses. So in terms of U1 it is equal to 0. Second body is at rest. So ut is equal to 0. Something into 0 is equal to 0. 0 plus 0, 0. And the first body must be come to at rest after collision. The velocity of the second body, in case of velocity of second body after collision, u2 already rest, so it's a 0. Masses are same, so it's a cancelled. v2 is equal to u. That is, one body is in motion, another body is at rest. In case of one-dimensional velocity collision, first body comes to rest after collision, second body is moves with the velocity of first body before collision. The third case is if second body is at rest before collision, then what is the velocity of the first body and second body after collision? Velocity of the second body is at rest. So simply we can write as m1 minus m2 by. Here the masses are not same for different masses. So m1 plus m2 u2 u1. u2 is 0. So something into 0 is 0. So velocity of the second body after collision v2 is equal to, from this expression u2 is equal to 0. So from this one, 2m1 divided by m1 plus m2 u2 u. ut is equal to 0. So both the bodies having their velocities. That means the second body is at rest. First body having a velocity, second body at rest. During collision, exchange of momenta, that is the momentum is transferred by the first body to the second body. Some part is retained, some part is transferred. So I want to find out the momentum retained by first body and momentum transferred by the first body to the second body. From this expression, I want to explain the momentum retained by first body and transferred by the first body to the second body. So from this expression, clearly m2 is equal to 0. The first body mass is m1, velocity is u1. Second body mass is m2, velocity is 0. So before collision, the momentum of a body, first body is taken as P and the kinetic energy is taken as a K. The momentum of a second body is 0 and the kinetic energy is also 0. So the before collision, the momentum of a combined system of a two particle system is taken as a P and the kinetic energy is taken as a K. That is, K is equal to here, P is equal to m1 u1 and K is equal to half m1 u1 square. Simply here, P is equal to m1 u1 before collision and the kinetic energy K is equal to half m1 u1 square. That is the initial kinetic energy of a system before collision. So after collision, the momentum of a first body P1 is equal to m1 v1 and kinetic energy taken as a Ke1 is equal to half m1 v1 square. Momentum of a first body after collision is m1 v1 and the kinetic energy of a first body after collision is half m1 v1 square. The fraction of the momentum retained by a first body